Hello everyone. Let's begin with something we all experience: motion. Look around you: birds flying, buses moving, leaves falling, even clouds drifting across the sky. Everything seems to be in motion. But here's a curious thought. Have you ever sat in a moving train and felt like you were at rest? That's because motion isn't just about moving. It's about what you're moving with respect to. And that brings us to one of the most important ideas in physics. Motion is always relative. So what does it really mean to be at rest? A body is said to be at rest if it does not change its position with respect to its immediate surroundings. And motion, that's when the body does change its position with respect to its surroundings. Sounds simple, right? But here's the twist. Both rest and motion depend on the observer. If you're sitting in a bus and the person next to you isn't moving relative to you, they seem at rest. But for someone outside, both of you are moving together. That's why we say rest and motion are relative concepts. They depend on your point of view. Now that we understand motion, let's zoom into a simpler type: one-dimensional motion. It's when a body moves along a straight line, no zigzags, no curves. This type of motion is also called rectilinear motion. Think of a train on a straight track, or a ball dropped vertically. They're perfect examples. In one-dimensional motion, there's no sideways movement. The body either moves forward or backward along a straight path, like moving on a number line. And this type of motion is extremely useful. It helps us build our understanding before we move on to two- and three-dimensional motion. So how do we represent one-dimensional motion? We use graphs, simple but powerful tools. On such graphs, the x-axis usually represents time in seconds, and the y-axis represents position or displacement in meters. For example, if we observe the motion of a pebble falling straight down at different time intervals, we can plot its position every second. Now let's tackle a common confusion: distance versus displacement. Let's say a person walks 10 meters forward and then comes 5 meters back. The total path covered, 10 plus 5, is the distance. It depends on the path and is always positive. But displacement, that's different. It's the shortest distance from start to end here, just 5 meters forward. And since direction matters, displacement is a vector quantity. So, distance is total path traveled equals scalar quantity. Displacement is net change in position equals vector quantity. We use small s for distance and s with an arrow over it for displacement to show the difference. Let's solve a quick example to make things clearer. A person walks from point A to point B, a distance of 10 meters, and then walks back to A. So what's the distance? It's 10 meters to go and 10 meters to return, so 20 meters. Now, what's the displacement? Since the person ends up where they started, the initial and final positions are the same. That means displacement equals 0 meters. This shows how motion can cover real ground, but still result in zero displacement, like when you walk in a circle or run a lap around a track. Let's quickly go over what we've learned today. Motion and rest are not absolute. They depend on the observer's perspective. A body at rest doesn't change its position with respect to surroundings. A body in motion does. One-dimensional or straight-line motion helps us understand more complex types of movement. Distance measures total path. It's scalar. Displacement measures shortest path in a specific direction. It's a vector. These concepts form the very foundation of kinematics, and we'll build on this in upcoming topics. I hope today's lesson helped you see how physics isn't just in textbooks. It's in your footsteps, your commute, and even a falling leaf. See you in the next session with another exciting concept in motion.